Additive manufacturing works always from the application backwards, user-centric.
If we're not helping customers visualize the potential of this new technology, it won't happen naturally.
We came together with the new development from HP for the much more productive 5200 series system and the Siemens software solution.
A deadline is the mother of innovation. This started a few months before we launched the 5200, and that gave us a couple of months to come up with something.
So we got our teams together for a workshop in Vancouver, Washington, and we spent 3 days together, locked in a room.
Well, we talked about structures in an automobile that you could optimize for crash protection. We talked about cooling in batteries.
All that while we were brainstorming, there was this unassuming cooling duct sitting in the middle of the table. Finally, one of our guys picked it up and said, "What is this?"
Of all the possibilities, we landed on a duct, which is part of our own HP 3D printing devices.
To maintain the reliability for that printhead, we need to keep the ink cool, and that's done through the cooling system. The duct was an integral part of connecting the fans to the cooling of the pen. We already had a 3D printed version which combined 6 parts into one, but we wanted more. We wanted more performance from the general flow, and we wanted more balance between the two printheads.
The topology optimization will look at which parts of that design space help to gain our engineering objective, which is minimizing pressure loss, and basically then remove those parts which are detractors. We had a super large amount of recirculation, so basically the air was going in circles, losing a lot of energy. Now we have basically 4 distinct flow guiding veins which take out the swirl and immediately force the flow to go straight forward instead of going in circles.
So it was really hard to wrap your head around that geometry when we first got it from Julian, just because it was so different than what everybody was expecting. So I had to take that geometry, smooth it out, create a thin-walled part from that we could use to create the duct part. I mean, when you talk about how the original duct was designed, where a person had to manually make every radii, every extrude, every little feature on that part, with a simulation-driven part, you don't have that. The simulation makes the geometry for you, and that is a much faster process than trying to design all that by hand.
As the design was shaping up, and it defied whatever everyone, including me, was expecting it should look like, with the tongue sticking out.
I was pretty stunned when I learned that the software predicted a 22% improvement in airflow.
22%, that seems pretty high compared to our baseline. But again, Siemens, they are the simulation experts. We had to go back to the physical world and actually test that new design is going to deliver more airflow.
Sure enough, when we went back and measured, the Siemens design duct improved the airflow by 22%, just as the software predicted.
On the other side, normally you need months to develop these, and here we have reduced the innovation cycle time by 75%.
Which is quite remarkable if you think about it, because it's not like you landed on a design. We landed on the most optimum design for that particular problem.
Getting the optimized design was just half of the battle. The next part of the challenge was transitioning that design into the AM factor where we could produce it at scale.
A lot of companies only have experience with lab-like environments. So they have 2 or 3 printers, they know how to operate it, but they actually don't know how it will look like if they ramp it up with more printers.
We are able to show the full simulation up to 100, 200, 300,000 parts by utilizing a digital twin, and then start with different scenarios to optimize how to improve it.
For the end state, with 300,000 parts, we would need 36 printers and 6 workers.
We can take an application with improved performance from the flow optimization, show that we can produce it in the industrial printing system, and this is unique in the world.
It kind of tips engineering on its head a little bit. Engineers no more should really be focused on the form and what the product looks like. They should be focused on what the product needs to achieve.
We've got a part now that has done something that I don't think anybody else in the industry has done. And when you combine that with HP's ability to industrialize additive manufacturing with their printers, it's a really strong solution.
Interest in this type of solution has been outstanding, and not only in the automotive industry, but also consumer goods. Think about refrigerators, air conditionings, vacuum cleaners.
What I'm most fond of from this project is going into meetings and handing the duct to a CXO and having them hold it and be inspired by what was possible with additive manufacturing and generative engineering, and wanting to be able to find a way for their company to be able to repeat this kind of success.